Hello, student. Welcome back to this topic of digital to analog conversion. So, in the last class, I discussed the resistive divider network, and also we came to know what are the drawbacks of that circuit. And now I am going to explain another type of network which converts the a digital signal into a equivalent analog signal is called as the binary ladder network. So this binary ladder is a resistive network whose output voltage is a properly weighted sum of the digital inputs. Such a ladder designed for 4-bit is as shown in the figure. So this is the ladder network designed for the 4-bit, and this is a 4-bit circuit because 4 inputs are there, 4 digital inputs are there, and it is constructed of registers that have only 2 values, and thus overcomes one of the objections to the resistive divider network. So in the resistive divider network, in the last session, I have explained it is one of the drawback that the resistors used in the network are of different values. So that creates the problem of precision and accuracy. So that problem is overcome here because here only the 2 types of resistors are used. One is the 2R and another one is the R. So that is why it is popularly known as R2R, R2-2R ladder network. So A, B, C, D are the nodal points, and these are the inputs. 2, 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3 are the inputs, digital inputs. And the left end of the ladder is terminated in a resistance of 2R. This is the left end. So when you are going back from this node A towards this ground, so this is the left end. So this left end is terminated via this resistor, 2R resistor, and the right end of the ladder output is open circuited. So this is the right end. So here the ladder output is obtained. So it is open circuited or it is kept open. And the output voltage is always measured between this point and the ground. And let us examine the resistive properties of the network, assuming that all the digital inputs are at a ground. So beginning at node A, the total resistance looking into the terminating resistor is 2R. So you are here. I will show the other diagram. So this is the node A. The total resistor when you are looking towards the terminating end is the 2R, and the total resistance when you are looking towards the input end is also 2R. So that is explained here. So beginning at node A, the total resistance looking into the terminating resistor is 2R, and the total resistance looking out towards the 2 raised to 0 input end is also 2R. But these two resistors can be combined to form an equivalent resistor of value R as shown below, because these two resistors are are connected to the node A and other ends are grounded. You see, this is the 2 raised to 0 input. So we have assumed that all the inputs are grounded. That means this is connected to the ground. So this is connected to the ground. So therefore, between the ground and the node A, these two resistors are connected in parallel way. So therefore, since the resistors are equal, 2R, 2R, the effective resistance of this parallel combination is a R by 2, 2R by 2. So 2 get cancelled. So it is only R. So in this way, the effective resistance between the node A and the ground is simply R because of the parallel combinations of the two resistors 2R, 2R, and so their effective resistance becomes simply R. So the node A is simplified in this way. Similarly, we can simplify for the other nodes. Then when you are moving to the node B, it becomes 2R. This R plus R becomes the 2R, and here again 2R is there. And this input end, that is 2 raised to 1 position or bit, is also grounded. That means it is connected in this way. So again, this 2R and 2R becomes parallel, and their effective resistance is R. So that is written in this way. So the circuit is reduced to uh, this part, this stage. And now you are moving to the node C, and this R is the R, the resistor R, which is here, and therefore they are in series. Now these two are in series, so the effective resistance of these two is 2R, and this is 2R. And this bit 2 raised to 2 bit is also grounded. So again, these two R and these two R are in parallel, and their effective resistance is R. So you are coming to this point. So you are here at node C, and these resistors are reduced to simply R because of the parallel combination. So then you are moving to the node D, and this R and the effective resistance of this is also R, and again these two are connected in series, so their effective resistance is 2R. And as we have assumed, this bit 2 raised to 3 bit is also grounded. So this 2R and this 2R is again, they are parallel, so their effective resistance is R only. So in this way, we can continue this procedure for simplification. And for this stage, I can stop. And if I stop, it becomes R plus R. R plus R is 2R. And I am getting an equivalent circuit. I am getting an equivalent circuit like this, or the reduced circuit, or the equivalent circuit like this for this node D. So it is clear from the our simplification that the total resistance looking back from any node, back towards the terminating resistor or out toward the digital input is 2R. So this point is clear here. So for any nodes, just now I will explain this point for the node D. So for this node D, when you are looking back towards the terminating end, the total resistance is 2R, and when you are looking out towards this input end of 2 raised to 3, it is also 2R. So this is true for all the nodes. This is true for all the nodes. So this is for node C. You can see for node C, uh, the total resistance when you are looking back towards the terminating AND is 2R, and the total resistance when you are looking towards the input AND is also 2R. So in this way, this statement holds good for all the nodes present in the circuit. So that is the meaning, and try to understand this very important line that the total resistance looking from any node back toward the terminating resistor or back toward the terminating resistor or out toward the digital input, or this is the out toward the digital input is 2R. So this point is clear now. And notice that this is true regardless of whether the digital inputs are at a ground or at a plus V volt. So this just now we have analyzed the circuit for the digital inputs at ground. In the same way, we can show that this is true when the digital inputs are connected to the voltage source. We can use the resistance characteristics of the ladder to determine the output voltages for the various digital inputs. So now we can analyze this resistive properties of this ladder network for a given digital inputs. First, assume that the digital input signal 100, 1000 is given to the this ladder network. For this signal, binary ladder can be drawn as shown, and its equivalent is also shown. So the binary ladder network for this particular input, that which is 100, is like this. So as I told in my earlier class, uh, this is the MSB. One is in MSB position, and this last 0 is in LSB position. So that is why you have to start identifying the bits from right. So it is 2 raised to 0 bit, 2 raised to 1 bit, 2 raised to 2 bit, 2 raised to 3 bit. That means 1 is under 2 raised to 3 bit. So these are 000 means they are grounded. They are grounded. So you look at this diagram. So these are look at this diagram. So this is the 2 raised to 0 input bit is there, but it is having a value 0. That means it is not connected to the voltage source. It is connected to a ground. Similarly, 2 raised to 1 position is also at a 0 level. That means it is not connected to source. It is connected to ground. Similarly, 2 raised to 2 position is also grounded, whereas this 2 raised to 3 position is not grounded because here 1 is there. So that shows that that the digital input is at a high position, or the digital output of that bit is at a high position. So here this 2 raised to 3 bit is at high position, so it is connected to the positive volt. Like that we have to mean. As this circuit is reduced earlier uh, step by step, so the equivalent circuit of this is written in this way, because all these are connected to the ground, they are parallel. We have to go on reducing. So lastly, you will get this as a 2R. This whole thing gets reduced to the 2R, and this 2R is there towards the input end. So therefore, this is the equivalent circuit. So from this equivalent circuit, we can write. So I will rewrite this equivalent circuit in this way. Because this is the point nodal point D, and so this and this end is connected to positive voltage. So you can see here this is connected to the positive voltage, and other end is connected to negative. So this circuit means between this point and ground, you have to mean that there is a battery source like this. So a battery is connected here, and so I will analyze this circuit now. The total current I is equal to V divided by 2R plus 2R, because the total current, when you determine the total current, it is equal to the potential of the battery divided by the net resistance of the circuit. So it is very clear from this that the net resistance is 2R plus 2R. So this is the total current. Then voltage at node D. Voltage at node D here at this point is written as a VA is equal to I into 2R, because when I measure the voltage at this point, I will keep the positive terminal of the multimeter here, and the negative terminal should be connected to the ground. So between ground and this point, what is the net resistance? 2R. So according to Ohm's law, it is V is equal to IR. So I is the total current flowing in the circuit. So I can write VA is equal to I into 2R using the just Ohm's law. And now you put the value of this I from this equation. So that is V divided by 2R plus 2R into this 2R. Simplify. So this is V into 2R divided by down. It is 4R, because it is 2R plus 2R. It is 4R. And now RR get cancelled. 2 ones are 2 twos are. So you are getting V by 2. So therefore, VA is equal to V by 2. That means when the MSB is connected to the source, voltage source, and all others are grounded, the voltage produced by this ladder network is V by 2. Thus, a 1 in the most significant bit, which is called as the MSB, in 2 raised to 3 position, will provide an output voltage of plus V by 2. Similarly, the output voltage due to the second MSB is given by VA is equal to plus V by 4. And suppose if you want the next MSB, means the third MSB, for that it will be VA is equal to V by 8. Like that it continues. So this procedure is adopted for all bits, and output voltages are calculated, and the list is given in the table below. So this is the output voltage list for this binary ladder network. The MSB, just now we saw that the MSB produces a binary weight. Its binary equivalent weight is 1 by 2. So it produces the output voltage of V by 2. The second MSB produces V by 4. Third MSB produces V by 8. And fourth MSB produces V by 16. Dash, 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 dash is continues. And for the nth MSB, it will be 1 divided by 2 raised to n, or it is equal to V divided by 2 raised to n. And since this ladder is composed of linear resistors, it is a linear network, and the principle of superposition can be used. This means that the total output voltage due to a combination of input digital levels can be found by simply taking the sum of the output levels caused by each digital input individually. So in equation form, the output voltage is given by VA is equal to V by 2 plus V by 4 plus V by a dash 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 V by 2 raised to n. So these are the digital outputs of individual inputs, and to get the net output voltage, we have to sum all these things, where n is the total number of bits at the input. Our equation can also be written in convenient way as VA is equal to V0 2 raised to 0. This is for the LSB, V1 2 raised to 1 for the first MSB, V2 2 raised to 2 for the second MSB, V3 2 raised to 3 for the third MSB, last dash 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 like this divided by 2 raised to n. So this is the done according to the principle of superposition, and where this V0, V1, V3, V2, V3 dash dash or the digital input levels. For getting constant output voltages and to maintain the ladder in a good balanced way, a unity gain non-inverting op-amp can be used at the output stage of the ladder network. So for getting the constant output voltages and to maintain the ladder in a good balanced way, a unity gain non-inverting op-amp. Unity gain non-inverting op-amp means it is a buffer network, so that is generally used. So you can see here, this is the ladder network. At the output of this ladder network, this unity gain non-inverting op-amp is used. Unity gain means the gain of this op-amp will be same, means 1. So that input is equal to output. So that is why VA is the input here. Same VA comes out of this this amplifier as a VA. The only thing is that some good constant or stabilized output you are getting by making use of this buffer amplifier. So it has a very high input impedance, and the output voltage is equal to the input voltage. So this the advantage of this buffer gain is that it has a very high input impedance. So here the impedance is very high, so that helps this ladder network to function properly. Then and output voltage is also equal to the input voltage. So it is thus a good buffer amplifier, and will not load down the ladder, and thus will not disturb the ladder output voltage. So that is why the advantage is that load will be here. So if load is connected here directly, so that load may affect this ladder network. So in order to avoid that, this amplifier is used so that the load which is connected here will not disturb this ladder network. So that is the meaning. So this is about R2 ladder network, and this is a very important ladder network used in many circuits, and we have to understand this clearly. So this is the end of the R2 ladder network. In the next class, I will take up the another different network which converts the digital input into analog one. Thank you.